Hello and welcome back, everyone. We're up to chapter 3, section 2, and as you can see, we're going to talk about extrema and the first derivative test. And if you haven't guessed by now, we're finished with finding derivatives. What we're going to do now is use derivatives. So all that hard work you've been putting in chapter 2 in particular is coming to fruition. So let's use that first derivative test and see what we can find out. By the way, extrema is not some kind of an exotic dish that the French make. So what do we intend to do? Well, occurrence of relative extrema, and don't get too unexcited about that. It just means highs and lows. Where are the high y values and where are the low y values in certain intervals. Not everywhere, just certain intervals. We're going to use the first derivative test to find those relative extrema, in other words, extrema within certain intervals, and then extend that to absolute extrema on closed intervals. Last of all, most importantly, we'll build up to finding minimum and maximum values of real-life models and interpret those results. It's the interpretation that really gets you the results from calculus. So here we go, relative extrema. I'll give you a little bit of a hint in addition, but so you're going to look at points where the function changes from increasing to decreasing, or vice versa. We talked about that in section 1, about increasing and decreasing, a pretty simple concept. And we're going to find those points. At the points where it has a relative extremum, which just means extrema singular, and so on. Relative minima, relative maxima. It's exactly what it looks like or sounds like. Okay, here's a picture for you. We've got a function. There's our function graphed out there for you. You can see what's happening to the y values. It's the y values that tell us whether something is increasing or decreasing or staying the same. And you can see for yourself what's happening to the y values. Going up, going down, going up again, and where they hit the high point or the low point are those relative extrema. And relative means not everywhere, but just in a certain range. So here we get something that looks a little bit exotic, but relax. So we're going to say we've got a function, its name is f, and it's defined at some number c. That's your x value. F of c, remember this is talking about a y value. Y equals f of c. So you take the x value as c, put it in function f, and what do you get out? You get a y value. That's what this really means. Now you've got an interval. These are the x's. And the x's range from a up to, but not including b. It's an open interval. Notice the parentheses. Now it says c is somewhere in the middle between a and b. And to be a relative maximum means that value of y is bigger than all the other values, or at least equal to, for any x that you find in that interval. Now I'll repeat that even though it's pretty much the same for the minimum. So f of c, remember that's an x value is c, you put in f, you get a y value. That's a relative minimum on that interval going from A to b if that c is smaller or equal to any other y's you find in that interval. That's a relative extremum because we're limiting it to values of x from a to b. And we're saying that an x value of c, whatever that might be, 2, 3, 17, 32 over 5, whatever it is, that's what gives us the either high or low value within that interval. Now, here's where we get something that's really important about this. If f has a relative minimum or maximum at that particular value of x, then it's a critical number of f. And that means also that f prime of c, or the derivative at c, is either 0, important, or undefined, that's important. Those will give you critical values. That's why we use a c, because it represents for us critical values. So let's see, how do we use that? Well, here comes the here comes the first derivative test. So first of all, we've decided c represents a critical number. Remember, that's an x value of c. And the first derivative test allows you to classify it as a relative minimum or maximum or neither. All three are possible. So here we go. We've got the first derivative test, and of course we're using the first derivative. If it's negative to the left of c, that means it's going down, and it's positive to the right, that means it's going up. And what you've got is a relative minimum. In other words, it went down until it got to c, and then went up afterward. All that means it's the smallest value of y in that interval from a to b. The relative maximum says just the opposite. If your derivative is positive to the left, that means it's going up. And then after x equals c, it goes down. Then you've got a relative maximum. Well, that should make sense. Draw a small picture for yourself. That'll really nail it for you. On the interval, if it's positive on both sides or negative on both sides, then you don't have a maximum or a minimum, relative or absolute. So this is what it looks like. We use our old friend, the parabola. Notice that on the left-hand side, you've got a negative derivative. That means it's going downward on the left-hand side. There is our c, that's a critical number. On the other side, it's going up, so it's positive, and that gives you a relative minimum. See, the y values are smaller than all the other y values that we're looking at. Next, if it's positive on the left, that means it's going up, and then later it's going down. You've got a critical point between them, and of course, as you can see with your eyes, it's a relative maximum. Now, relative because we're not looking at this part over here. No. We're not looking at this part over here. No. We're only looking at this part in here, and this is the maximum value that graph has in that interval, and over here, it's the smallest value in that interval. Next, now we'll get to some other items. Here's one where it's positive on the left. Here's our critical value. We've got a positive derivative on the left, positive derivative or slope on the right. That means it doesn't have a minimum or a maximum. And also, If it's negative on both sides, then this isn't a minimum or a maximum in that part of the graph that we're looking at. So here's how you do it. First, find the derivative of f. That's not too much of a surprise, right? Second, find the critical numbers of f. Well, the critical numbers are going to be where the derivative is 0 or it's undefined. Third, you're going to test the derivative at an arbitrary number. Arbitrary means you get to choose. It's going to be in those test intervals which are marked off by those critical numbers. And we'll get to an example. But basically, the critical numbers split the number line into several sections. Imagine you're using a knife and you're slicing up the number line at the critical numbers. Inside those intervals, you pick any number you like and put it into the derivative. Next, for every critical number, use the first derivative test to decide whether it's a relative minimum or a maximum or neither. And as you'll see coming up, a good way of doing this is to make a small table that has those critical numbers and those intervals, and you can test it with that table. So here we have an example. This will nail it, I hope, for you. We've got a function f of x, and it's x to the fourth minus x cubed. That makes it easy to differentiate. So what we're going to do next is take the derivative of that function. Look familiar? There's the derivative of that function. First derivative, of course. We can also factor that. That makes things a little bit easier because we're going to set this thing equal to 0 and find out which x's give us zeros or undefined. We can see that it's got two critical numbers, 0 and 3/4. Now what does that do? Here's your number line. And here's one critical number at 0, another critical number, let's say it's critical number 1, critical number 2, this one's at 3/4. Also take note that that derivative doesn't have any undefined values. This value right here never becomes undefined. And you might take note that the undefined part, that's when the derivative has a denominator that becomes 0. That's what makes it undefined. Anyway, we'll see one with that coming up. Next, we've got these two numbers. We've got the 0 and the 3/4. It splits the number line into interval number 1, negative infinity up to the first critical number, interval number 2 between the two critical numbers, and interval number 3 from the second critical number on up to positive infinity. Excuse me. That covers all the numbers in the number line. So these are the intervals. 1, 2, 3. Next, what do? You pick some number in that interval. You can pick anything you like. So if you like the number -2 or -3 or -10, you can use that. The person who wrote up this slide decided the test value, -1 looked good to him or her. In the second interval, we need something between 0 and 3/4. Well, 1/2 is an easy one to pick. So pick that one. And in the third interval, 3/4 to positive infinity. We could have chosen a 9 if we'd liked. 1 is in there, and it's easy to work with. So those are our test values. We're going to put those values into our derivative and see what we've got. So here's the -1, put in the derivative, and we see what we get. We get a -7. All we care about, we don't care about how big it is or how small it is, just whether it's positive or negative. Since it's negative, it tells us that in that interval up here, the function is decreasing. On the second one, we put that test point into the derivative. We get a -1/4 for a value that's negative. That means that this function, f, or this derivative, is decreasing because you get a negative number here, and that's anywhere in this interval that we found by critical points. Third, from 3/4 to a positive infinity, we picked a 1, we put that in the derivative, we get a +1. So because it's positive, not because it's 1, because it's positive, that means the function is increasing in that interval, everywhere in that interval. That's what we wanted. What we wanted was increasing, decreasing, or whatever that function is doing. Just find those intervals with the critical points, get some test values, your choice, as long as they're in the interval. Find out what sign you get for the derivative, and that tells you whether the function is increasing or decreasing in that interval. So, from that we can learn that f has a relative minimum at 3/4. And here's a picture. This is what our function, this is our function that we've been working with for a few minutes here. Notice that our derivative is negative here because it's going downward. Continues to go downward. When it starts going upward again, when it goes from decreasing to increasing, that's our first derivative test going to work, and we know we have a relative minimum because it goes from decreasing to increasing. If we were going from increasing to decreasing, we'd still have a relative extrema, but it would be a maximum. And what is that actual relative minimum? Just take that number where it's switching from decreasing to increasing, put that number in for f, that's our function, and find out what the value is that we get for y. That's your relative minimum. And also take a notice that the other critical number, 0, didn't give us a relative extrema because the derivative is negative on both sides. It has to change from negative to positive or positive to negative for us to get extrema. So how about absolute extrema? Well, we're partway there. Let's go the rest of the way. The terms minimum and relative maximum describe the local behavior. In other words, on an interval. The absolute maximum or minimum has to do with the entire graph of the function. So here's the definition. It's an absolute minimum if this value of f, that's the y value, is less than everything else on that interval. It's a maximum if it's greater than all the other values or equal on that interval. Got a few extra slides in there, sorry. So make sure you understand the difference between relative extrema and absolute extrema. Absolute extrema means everywhere on that graph. Relative extrema means on just parts of that graph. So here's an example right here. We've got a function and we're looking at it from A to B. Those are x values. Now you can take a look at this value right here. If we only look at this section of the graph, that's the highest. If we only look at this section, this one's the lowest. But this maximum over here isn't the maximum for everything on that graph, because this is actually higher. So when you're looking for the absolute, here, write this down. When you're looking for the absolute maximum or minimum, make sure you check the endpoints. Because even though you might have a relative maximum or minimum on that interval, they might not be the absolute maximum or minimum. Make sure when you're looking for absolutes, you check out the endpoints. You got that down? Okay. So the relative maximum, that's the one over here, is not the absolute. The absolute one turns out to be at one of the endpoints. And according to a theorem, and we won't go into proving things, that's not what we do in this calculus, a continuous function, if it has a closed interval, has to have both an absolute minimum and an absolute maximum on that interval. It will have them somewhere. It might be inside at one of these spots, or it might be one of the endpoints. So always check your endpoints. There's your extreme value theorem. It says as long as f is continuous, it's not jumping around, then it has a minimum and a maximum within that closed interval. Notice closed interval, that means we're including A and B. When we were talking about relative maximum and minimum, we talked about the open interval A and B, which did not include the endpoints. But when we're talking about absolute maximum and minimum, we're talking about a closed interval. We have those endpoints. We have to check those out because those might be absolute maximum or minimum. Let's look at the critical numbers and the endpoints. So here are the guidelines. Get the critical numbers of f in the open interval using the derivative, of course, first derivative. Find out what the value of f is at each of the critical numbers. Evaluate f at each endpoint as well as the critical numbers. And the smallest is the minimum, the greatest is the maximum. That's pretty simple. So once you get 1, 2, 3, you're looking for the minimum and maximum, just look at the numbers. So let's take a look. Here's a closed interval, 0 to 5, and we've got a function, x squared minus 6x plus 2. We want to find the minimum and maximum values. By the way, if you're thinking ahead, yes, we're probably going to be talking about things like cost, revenue, profit, just to get a firm grounding on these things. So, first of all, we're going to differentiate it because we need to find the critical points. There's the derivative. What are we going to do? Check with two things. See where it's equal to 0 and see where it's undefined. Well, you can take a look at that and you can tell there's no denominator, so it's unlikely to be undefined, but set it equal to 0. And there's a critical point. It's the only one, so it's going to split the number line into two intervals. So we've got the endpoints and the critical number. One of those is going to be the maximum or minimum. So we take the function value, not the derivative, the function value at those points, the endpoints and any critical points in between. We see which one's the biggest. Of those three function values or y values, 2 is the largest, so it's the maximum. -7 is the smallest, so it's the minimum. That easy. And you can see on the graph what we just found using our small table. We found that we had a minimum, we had a maximum, minimum there, maximum there. We checked the endpoints. This one in particular wasn't the highest or the lowest, so it's not a maximum or a minimum. Remember, check the endpoints, not just the critical points. Okay, we'll wrap this up with an application. And that's one of the most common applications of calculus. You might not realize that, but that's very important for business. So let's go with fast food. We're selling hamburgers, and here's our profit function. We might put P of X. And we've got an interval, a closed interval, notice, because we've got the equals on both sides. Interval from 0 to 50,000. We want a maximum profit, so we're going to be looking for where the critical points are. When we get those, we're going to check the function value at the critical points and the endpoints. See which one has the largest value. So let's see what sales level gets us that maximum profit. So first of all, we need a marginal profit function. That's the derivative of the profit function. So we take the derivative of our function, set it equal to 0 to critical points, solve for x, and our critical point is 24,400 hamburgers. That's our critical point. Remember, we've got endpoints too. So you can see here that here's our 24,400 hamburgers. Here's the left endpoint at 0 hamburgers, and the right endpoint at 50,000 hamburgers. Which one's the biggest? Well, our function value is largest up here. Here's our maximum. So put the 24,400 into the profit function. And our maximum profit is $24,768. Well, I hope you followed all that. If not, you might want to go back through it. Maybe even take a look at the slides yourself. Try some exercises and bring your questions to class. Well, with that, I'll say goodbye to you for now. See you soon.